Now I'm going to do the presentation of my final project. My final project is about super resolution. I came up with this idea from assignment 3 because in assignment 3, the main purpose is to build a model with autoencoder and CNN. We have a 28 times 28 picture, and from the encoder it goes to 7 times 7 embedding, and then we have the decoder. We generate a 56 times 56 picture, and each time we do the upsampling for this picture, and it get bigger once and twice and third, then you will get 56 times 56. And here is the result of these pictures. Because the question says the black and white picture will get better result because I think it's more simpler. So I use black and white picture, but the result is like blur and very bad. I cannot tell whether it's a whatever it is. You cannot say this is a cat. So I'm gonna redo this assignment and do it to make it a real super resolution project. Here is my final. First is the data implementation. I use the data the same as we have in assignment 3. And we use the data. Here is the transform. I transform the picture 28 times 28 to 448 times 448. And now I'm going to use train test split. Here we need to have a validation set to check when we stop training. And here is the model. And for this model, I'm not going to use the autoencoder because I'm not going to add anything to the embedding. I'm just to get bigger picture from each time by pixel shuffle. I'm gonna talk about pixel shuffle later. And for each time we get it like bigger twice, times 2, times 4, times 8, times 16, and 28 times 16 is 448. And the difference between this model and the assignment 3 model, first, this is not black and white model, so it had 3 channels for each picture, and also I added ResNet, which will solve the gradient explosion or gradient vanishing the problem. So and also here, this is the main part. I use this function. But in assignment 3, I use upsample function. Upsample is a traditional upsampling method that is efficient, but it may introduce artifacts. But the pixel shuffle is a parameterized and efficient upsampling layer that better preserves details and is widely adopted in super resolution tasks. So, and this one really works well. I have tried to do it like pixel shuffle 8, but actually the result is not like this. Each time we make the picture getting bigger twice. And here I also use Leaky ReLU because for ReLU, if the value is negative, we will lose the information, all the details. But if we use Leaky ReLU, for example, I set 0.1. Here it will have some details if the information is really important. And here I need to initialize weights because I'm not gonna do just one model. I will explain this later. And here is the trainer. We set up the trainer. We call this enhanced super res trainer. Actually, this is an algorithm called ESRN or ESR or whatever it is to do the super resolution. And here we set the input for the validation set, and we train the model. Because here I'm gonna train model with different loss function metric. Here is a PSNR and also SSIM. I'm going to introduce, this is my final project paper. So here is a PSNR. PSNR is a commonly used to measure the quality of reconstructed pictures in comparison to the original. It calculates the logarithmic scale of the inverse of the MSE between the reconstructed and original images. And here is the formula of PSNR, and also we have SSIM, structural similarly index measure. And here is the function of SSIM. SSIM designed to provide a more perceptual relevant assessment than PSNR. Keep going to this, and here is the function. And now I'm gonna train the model. To train each model first, we set up this because wait, I believe there shouldn't be one because because when we do the loss function, we want the value to be like 0. For example, we don't want any loss. So we want the value to be smaller, but PSNR is the value to compare whether the model is good. If it's good, you will get higher value of PSNR. So we take the negative sign, but we don't need to add 1 minus. I forgot to cancel this. I add 1 minus because I want to check SSIM, because SSIM is kind of like a model that it's kind of like you will get value from 0 to 1. Sometimes we get negative value, but I'm not gonna have negative value right here. It's a very rare occasion to get negative value. So we get value from 0 to 1, and if we get 1, it means these two pictures are exactly the same. And if we get 0, it means the picture has no like correlation. So like we want to have higher SSIM, which is we want it to be close to 1. So I set 1 minus SSIM because it seems like a loss function. And here I set up all these train models, and we can see this is the result. This is the result for the normal MSE, and we can see the loss drop really quick before 5. And also here the PSNR for the impulse, we need to set up like 20, 22 or 23. It keep going down, and we can, I think from this area is okay, because even if the slope decreases, but the validation loss is still decreases. So we're not gonna have like a very serious overfitting issue right here. And also for this one, even the slope doesn't really change here. The validation loss is still going down. And also for the SSIM, we can see that it's still going down. So we may take more approaches. And actually, so I chose 20, 20, and 34 right here. Actually, I didn't choose 34 from this picture. I did it like several times, but I'm not gonna put it everything here because I use another block to calculate the 34 number because I'm not gonna train all of those again. And for this one, for the first normal MSE, I use 20 because like you can see, maybe you're gonna just use 5 right here, but after I use 5, I got a result that the image is kind of like black and white right here in MSE. So my guess is the loss function is not sensitive to the color. Maybe the black or white, they can make really good loss because it has the good shape, but not even if the color is not the same. So like for this part, it's still black or white. You need to train more. So I just choose 20, and I think the result is acceptable. So I chose 20, 20, and 34 for all these. 20, 20, 34. Here you can see the slope is getting like good. Yeah, 34 is kind of good, even if the trend is still going down. Then this is the result. This is the result. First is for MSE, and we can see that this one is much better than this one. This one is blurred, and this one is actually good. I mean, compared to this one, and we can see there's a cat. We can notice this obvious a cat, and compared to all these three models, I'm sorry. Compared to all these three models, you can notice that SSIM did the best job among all these three. We can see the eyes and nose and ears very clearly with the details, but these we can, for example, here's the example. This is the front face of a cat, and these two are the front face of the cat. We can see the quantity of pictures and also the pixels, which is much better than this. And for this part, I think is better than the normal MSE. For the normal MSE, it's kind of blurred. So I cannot like quantitatively compare these three because it use different loss function. I can just tell you my feelings, and you can also check the feelings. I believe you may say this one is much better, but there's another problem that if we compare especially this one, because for the set there are only dots and cats right here, you cannot distinguish other things like human or whatever it is. Like for this one, I don't really think this is a cat. It's more like a bird or a rat. So the thing it generates is, I don't know what it is. So I think this picture is kind of, I don't know what it is. So the result is not good. And for this one, we can see it clearly. There's a human with a blue shirt holding his cat, his white cat. And for the picture generation, it generated the cat really good, but for the human, it just don't know what it is, and even the color just changed. Is the skin color, but here is like a feather or something, fur, but not the skin. And also for this one, this is a hand. This is more like a skeleton. So yeah, it's not a hand. It's more like bones. And the color just changed. So I think this result is good, but we still have a lot of place to improve this one. So this is my paper. So the conclusion is, I think first we may use GAN because GAN can capture more details and it can generate more realistic pictures and reduce the noise. And also we need to, if we want better picture, we can definitely add transformers into this project, because transformers can get the global structures and detailed informations within the pictures and analyze all the informations much better than before. And also we can use VAE. Here I'm gonna, because my project didn't use autoencoder, but we can use autoencoder to do the picture better, because for the autoencoder we can add information to the embedding, so that when we like, for example, we have a lower pixel picture and we want to have a higher pixel picture, so there must be some more informations between these two pictures. So if we have a VAE and like more complicated neural networks, then we can add information to the original picture, and then we get a better picture. So this is the project. Thank you.